We're starting the third lecture for the second week, the course of communication systems. In our last lecture, we talked about line spectrum, and specifically we discussed one-sided spectrum in our last discussion. In today's lecture, we will be talking about two-sided spectrum. In order to move on to the two-sided spectrum, let us start our discussion from the Euler's identity. We know that Euler's identity relates this complex exponential function with sinusoidal functions. E raised to power plus or minus j theta is equal to cos theta plus minus j sin theta. So e raised to power j theta is a complex number for which the real part is cosine theta and imaginary part is sin theta. From this Euler's identity, we can separate out cosine function, which can be written in this form: cos theta is equal to e raised to power j theta plus e raised to power minus j theta upon 2. So this is representation of cosine function in terms of the complex exponentials. So now let us turn our attention to the sinusoidal example that we were discussing in our last lecture as well, that we have a sinusoidal function represented by this expression a cos omega naught t plus phi, where a is amplitude of the sinusoid, omega naught or f naught is actually the frequency, and phi represents the phase angle. If we use this identity, cos theta is equal to e raised to power j theta plus e raised to power minus j theta upon 2. So using this identity, we can transform this sinusoidal function into a complex exponentials. So if we transform it, so a as a constant, it would remain same, and cos theta would be replaced by this value as theta is equal to omega naught t plus phi. In this case, I have replaced theta to be equal by omega naught t plus phi at both places. So we have used this identity to represent our sinusoidal function. And if we separate out different terms, we can simply write, because this is a by 2, so this is actually a by 2, e raised to power j and phi, we can combine them together, e raised to power j phi. Similarly, e raised to power j omega naught t would remain same. Similarly, for this expression, e raised to power minus j phi and e raised to power minus j omega naught t. So from this representation, you can see that we can write this cosine function as sum of two phasors. These are two phasors as we discussed, and the interesting thing is that both of them, they are conjugate of each other. As we see that if we take conjugate of this function, we know that the complex conjugate of a complex number is same, except that the sign of the imaginary part gets reversed. So you can see that this is a complex number, and this one has is the same complex number with minus sign wherever j appears here. So these two phasors, they are conjugate of each other. Second thing to note, that you should see that the length of both the phasors is same, a by 2, which is actually half of the original length. The function a has the length a, so now the two phasors which are present in this expression, they have half of that length. Phase angle remains the same, j phi is here, and for the second phasor you have again the same phase angle but with negative sign. The important part is this one, e raised to power j omega naught t, and the other part, e raised to power minus j omega naught t. As we have seen previously that this e raised to power j omega naught t represents a rotation of that phasor. Similarly, e raised to power minus j omega naught t would represent the rotation but in reverse direction because of the presence of this minus sign. So we have a rotation in the reverse direction. So if we try to plot this phasor, so it would look somewhat like this. So actually our figure would have two phasors, and each of the phasor would be represented by the half of the length a by 2. You can see here. So we have another phasor at downward. The phase angle is negative of each other, so you can see that one phase angle is positive and the other phase angle is negative. And as both the rotational frequencies are in reverse direction, so one rotational frequency is represented as counterclockwise and other rotational frequency is represented as clockwise. Returning back to this expression, you can see that this term has a positive sign with the frequency term here. So if this is a positive sign, and similarly this term has a negative sign associated with this frequency. So from here this expression gives rise to the concept of a negative frequency. So if we try to plot the spectrum of this signal, we would see that we would be needing positive frequencies as well as negative frequency. The positive frequency would be used to represent this part, and the negative frequency would be used to represent the second part. And you can see that both of the amplitudes for both the frequencies, they are same, and they are actually half of the total amplitude. So the amplitude is actually equally divided on both sides, and the phase angle in both cases it remains same, but with opposite signs. So if I try to plot the spectrum or two-sided spectrum in this case, so it would appear somewhat like this. The amplitude spectrum would have two frequencies. One is f0, which is the positive component, and second is minus f0, and both of them have equal amplitudes, which is actually half of the original amplitude. So amplitude is equally divided, and you can see that it exhibits the even symmetry here. So around 0 you would see an even symmetry. Similarly, if we try to plot the phase, so again we would be having two frequencies. One is the positive frequency and second is the negative frequency minus f0, which refers to this part of the expression. And the positive frequency has a phase angle of phi, and the negative frequency has the same phase angle phi but with negative sign, so it would be having minus phi angle. So this is the line spectrum representing the sinusoid wave, and you can see that this spectrum now has both positive frequency as well as negative frequency. Therefore we generally call it a two-sided spectrum or a double-sided spectrum. So you should see that the line spectrum that we get now is a two-sided or double-sided spectrum, because it must include the negative frequencies as well, and this negative frequency is coming from the fact that we have an opposite direction, rotational direction for the phasor that we used to represent in the expression as well as in the phasor diagram. Secondly, one half of the original amplitude is associated with each of the two frequencies, that is the frequency we have plus f0 frequency and minus f0 frequency. One important thing that you should note, that the frequency of any real signal is always positive. We understand this thing, that the real signal has a positive frequency. However, in this case we are having a negative frequency as well. So this negative frequency is actually appearing in the double-sided spectrum because we are using a complex domain representation. We are not using a real domain representation. So we are trying to represent a real signal in a complex domain, and because of the representation of this real signal in complex domain, we get a negative frequency component as well. And of course both positive and negative frequencies, they should be included for the complete representation of the signal. So the representation would be incomplete if you only show positive frequency or only show negative frequency, because the complete description would involve both the frequencies. So in order to incorporate both the frequencies, generally whenever we mention any specific interval or any range in the frequencies, we use this modulus function, because this modulus function always have the concept of positive as well as negative frequencies. So a common notation in identifying frequency band in such cases is this one, that we use a modulus with the frequency variable. There are few important things that you should note for this case. Remember that we are talking about a real signal. So the signal that we are discussing is actually a real signal. However, we are transforming this real signal into a complex domain, and by transforming into complex domain, we get negative frequency, and eventually the spectrum that we get is a two-sided spectrum. So first thing is related to amplitude spectrum. You should observe that the amplitude spectrum has even symmetry. We can go back to this diagram. If you see this origin line here, so whatever shape you get at the positive frequency, the same thing is apparent at the negative frequency. So if you fold it, you will get the same overlapping. So this one has a positive symmetry here, the amplitude spectrum. Similarly, the phase spectrum has odd symmetry in the double-sided spectrum. You can go back to this diagram here, and if you look at this origin line, so whatever diagram you have at the positive frequency, we have the same diagram but in opposite direction. So this one is actually -5. So this gives rise to negative frequency in the spectrum. So the amplitude spectrum has even symmetry and the phase spectrum has odd symmetry. And of course, in order to have the complete representation of the signal, we need to have both parts, that is amplitude spectrum as well as the phase spectrum for the signal. But for the point of view of communication system, the amplitude spectrum conveys more information as compared to the phase spectrum. So in most cases, we only refer to the amplitude spectrum whenever we are interested in identifying the specific frequency contents in the signal. So amplitude spectrum is gives more information to us as compared to the phase spectrum. So therefore, in many cases, we only refer to the amplitude spectrum. So this amplitude spectrum will tell us what frequencies are present in the signal and in what proportion they are present. So in other words, this amplitude spectrum gives us the signal's frequency contents. So what contents are available in the signal, they are actually conveyed by using this amplitude this amplitude spectrum. Mathematically, any periodic signal can be represented as sum of sinusoids, and this is actually the case of Fourier series that you must have taken in your previous course. If we have any periodic sequence periodic signal, we can transform it into sum of sinusoids, and eventually we can easily plot the spectrum of that periodic signal. So let us take a simple example. Actually, this is the previous example that we used to plot the one-sided spectrum. So now we want to plot the double-sided spectrum of the same signal that we have discussed previously. So first I have transformed this signal into the standard form, the convention using our conventions. So this signal actually has three components or three frequencies. Here you can see first is 0 frequency, second is 20 frequency, and third is 60 frequency. So we have three frequencies here, and we can, using this expression, we can easily draw the spectrum. But for this particular case, we are going for the double-sided spectrum, and you should recall that in double-sided spectrum the amplitude is equally divided, means half amplitude would appear at the positive frequency and the half amplitude would appear at the negative frequency, whereas the phase has the odd symmetry and it's replicated at positive and negative frequencies. So if you see, if you try to plot the spectrum, so it would look somewhat like this. So the zero frequency has the constant amplitude, which is 7. Of course, 0 does not have any concept of positive and negative, so therefore the entire value 7 appears at 0, but the phase angle corresponding to 0 is 0, so it appears here. At the frequency of 20 Hertz, we have the amplitude of 10, but when we go to plot the spectrum, it will be divided into two halves. So you can see that the amplitude of 5 appears at the positive frequency and amplitude of 5 appears at the negative 20 frequency. Similarly, the phase angle related to this 20 Hertz frequency is 120 degree, and you can see that the phase angle appears here. This is 120 degree at the positive frequency. However, the phase angle at the minus 20 Hertz frequency would be negative of what you have at the positive frequency. So this will be minus 120 degree. And the third term is actually this 60 Hertz term, and with the amplitude of 4. And again, when we plot the double-sided spectrum, so this amplitude of 4 would be divided into two parts. So this 60 Hertz frequency is the positive 60 Hertz frequency has amplitude of 2 units, whereas the negative 60 Hertz frequency has the amplitude of 2 units. So the amplitude is divided into two halves. The phase angle here is minus 90 degree. You can see from this expression. So at 60 Hertz, the phase angle is minus 90 degree, and at the negative 60, the phase angle would be negative of this minus 90. So negative of minus 90 would be plus 90 degree. So you have this odd symmetry here in the phase spectrum. So this is how we can plot the double-sided spectrum for the signal that we have previously discussed. In order to have some practice on this plotting of single and double-sided spectrum, I would give you a simple problem. You try to plot the spectrum, both one-sided and two-sided spectrum for this signal Vt is equal to -3 -4 sin 30 pi t. So this is a homework problem for the students. You need not to submit it, but you should give it a try. So this concludes our discussion onto the line spectrum, and we have discussed both positive and negative spectra, how we can generate the positive spectrum and negative spectrum to represent our periodic signals in the frequency domain. So what important thing that we have discussed, this line spectrum actually comes from the fact that we are working on a periodic signal. So generally the periodic signal, they are represented in frequency domain using their line spectrum. What happens if you have a non-periodic signal? So if you have a non-periodic signal, those can also be represented in frequency domain. The same concept of frequency domain is also applicable to the signals which are actually non-periodic. However, the non-periodic signals, they do not have line spectrum or they do not have discrete frequency components. Rather, they have continuous frequency components. So actually their spectrum, they are continuously varying with respect to frequency. So both amplitude and phase, they change continuously when we go in the frequency domain. And this transformation from time domain to frequency domain is actually mathematically achieved using Fourier transform. However, we would not be doing the Fourier transform for most of the cases in our course, although I understand that you have taken a course signaling system previously, in which we have discussed how to calculate Fourier transform, but we will not be calculating because there are standard tables available for Fourier transforms and its properties. So whenever we need to use any Fourier transform of any signal, we would rather refer to the standard table and get the transform directly from that table. One conventional thing that we use in transform is that we typically use small letters to represent a signal in time domain, and capital letters to represent a signal in frequency domain, or capital letters are used to represent the spectrum of the signal. So if you have a time domain signal, so it will be represented by small vt, and its spectrum would be represented by capital V. So this is our convention that we commonly use. So you should realize that the continuous spectrum can also be plotted in both ways. You can plot the continuous spectrum as one-sided or two-sided as well. However, the most convention or most common cases in communication system is to plot the spectrum in two-sided. So we will be discussing only two-sided spectrum for rest of the course. So as an example, although I'm not going to do actual calculation of Fourier transform, but as an example of having a continuous spectrum, let us take a waveform which is illustrated here. This is a simple exponential signal a e raised to r minus bt for t greater than 0, and for t less than 0 it is equal to 0. So this is an exponentially decaying signal. If we transform this signal into a frequency domain by using Fourier transform, we would see that this is the transform of the signal, and we can represent this transform into standard form by multiplying and dividing by the conjugate of this denominator, and you would see that this is the transform of the signal. We can have real and imaginary parts of the signal. So this one gives the real part of the signal, and this is the imaginary part of the signal. As we have previously discussed, that the spectrum is actually provided in form of two different graphs. So we need to have two separate graphs, one for the amplitude of the spectrum, and second is the phase spectrum. So if we calculate the amplitude of this complex number, this one is actually a complex number, and we can calculate the amplitude, and we know that the amplitude is actually square root of real part squared plus imaginary part squared. So as we know both real and imaginary part, we can simply substitute it here, and we would see that the amplitude spectrum would come somewhat like this: a upon under root v square plus 2 pi f. Phase spectrum is actually tangent inverse of imaginary part divided by real part. This is the standard formula of complex number. So we can, using this formula, we can find the expression for the phase angle as well. So if we plot it, you would see that the amplitude spectrum would look somewhat like this. This is the first part, is the amplitude spectrum, and the second graph, this graph, is actually the phase spectrum. And you can see that the amplitude is continuously changing. There are no discrete frequencies, rather the change is a continuous change, and this continuity in change comes from the fact that the signal that we are dealing is actually a non-periodic sequence, non-periodic signal. So whenever we try to represent a non-periodic signal in frequency domain, we need to use a Fourier transform, and whenever we transform the signal in frequency domain, and we would see that the spectrum that we get from this transformation would be a continuous spectrum as shown in this diagram here. This is only one example of one signal of this complex exponential. Similarly, for other types of signal, we can calculate their amplitude spectrum as well as the phase spectrum. However, as I mentioned, that in most cases in communication system we are only interested in amplitude spectrum, and therefore in sometimes we all ignore the phase spectrum. But you should understand that in order to have the complete representation of a signal, we need to have both amplitude as well as the phase spectrum. So this concludes our discussion on to the different types of spectra that we use. And summarizing the discussion, I would mention only one point, that we have two types of spectrum. One is the continuous spectrum, which is obtained using the Fourier transform, and this Fourier transform is only applied to non-periodic signals. And second type of spectrum is the discrete spectrum or line spectrum, which is obtained using Fourier series, and that Fourier series is actually applied to a periodic signal. So this concludes our discussion on spectrum, before concluding our today's lecture, I want to discuss some important types of signal that are commonly used in communication system. There are variety of signals that are commonly used, and some of them we are familiar of, and we do not need further discussion, like sinusoidal signal. In fact, for last couple of lectures we are already discussing the sinusoidal signal. Similarly, another signal is exponential signal, for which the spectrum was shown in the previous slide, and another sequence is the rectangular pulses that are commonly used to represent bits and digital systems. Here we want to discuss few new functions or signals which are also very useful in analysis of communication systems, and we will be discussing these three functions, namely unit step function, signum function, and unit impulse function. So what is unit step function? Unit step function is mathematically defined by this relationship: u of t is equal to 1 for t greater than 0, and u of t is equal to 0 for t less than 0. The following graph, this graph shows the plot for this unit step function. You can see that for negative time the function has the amplitude equal to 0, and for positive time the function's amplitude is equal to 1. So it has a constant amplitude only, which is equal to 1. In a sense, the unit step function represent the switching operation, where you have switched from 0 to 1 at time t equal to 0, or in other words, where you have switched from off state to on state, because this 0 generally refers to the off case, and this 1 refers to the on state. So unit step function is actually mathematical representation of that switching operation. This function is very important in Fourier analysis and spectrum calculation, especially when we are interested in discussing causal signals. You understand that the causal signals, they generally start from t equal to 0. So and they do not have any value for t less than 0. So if we multiply any time function with u of t, eventually it will suppress all the values for t less than 0. So if you multiply by any function with u of t, so it will become equal to 0 for t less than 0, and for t greater than 0, of course it would have some value, which is also the property of the causal signal. So one way of representing the causal signal is by having u of t multiplied by that particular signal. Second type of function that we are going to discuss is signum function, or sometimes we call it a sign function, because it actually shows two different polarities or two different signs. So this sign function takes the value of +1 whenever you have t greater than 0, and it takes of value of -1 whenever t is less than 0. this is the plot of the signum function. It's plotted here. You can see that for negative time the function has the value which is actually -1, and for positive time the value of the function is equal to +1. In a sense, you can see that this function has an odd symmetry, so you can also exploit the property of symmetry whenever you are dealing with this signum function. You should also note that we can easily relate this step function with the signum function. The previously discussed signum function is here. So if we add 1 to the signum function, so eventually it will become twice of u of t. So u of t can be written as half of signum t plus 1. So we can easily relate this step function with the signum function as well. Okay, the third and the last function that we are going to discuss in this lecture is unit impulse function or unit impulse signal. The unit impulse function, or in mathematically it is named as Dirac delta function. The Dirac delta function is actually not a mathematical function. Strictly speaking, it's not defined like a function. Rather, it is defined on the basis of some rules. So this function delta t is actually defined in such a way that it satisfies certain properties. So it does not have any specific value, but it has to satisfy these two properties. First property is that the value of the impulse function is 0 for all times. So this function is 0 for all time except only one point, and that one point is actually t equal to 0. So the function exists at only one point. So all other points its value is 0. It exists at only one point, which is the point where the argument, this t, is actually becomes equal to 0. So I can write it that delta t is equal to 0 whenever t is not equal to 0, and whenever t is equal to 0, the delta t is not equal to 0. So this is one property, that the function exists at only one point, and the point is where this argument or this t is actually equal to 0. Second property is that the area under the unit impulse function is always 1. Is the area under the unit impulse function is unity. That means if we integrate this delta t function, we will get 1, because integration is commonly used to calculate the area under any specific curve. So if we try to integrate delta t, we would get 1, or area under the curve is equal to 1. Combining these 2 points, we can say that delta t has unit area, and that area is actually concentrated at only one point, which is t equal to 0 point, and there is no net area elsewhere. So the entire area is actually is concentrated at one point, which is t equal to 0. So I can write in this form as well, that if we integrate delta t dt, so this is actually equivalent to writing this delta t dt with the limit of minus epsilon to epsilon, where epsilon is actually only one point which is equal to 0. So I have represented it by, in terms of limit epsilon goes to 0. So we have -0 to +0 limit. So it's actually only one, it represents only one point. So at one point the area is represented as 1. So this delta function has unit area. If I try to geometrically represent the signal, the unit impulse function, so it is represented typically like this. You can see that the delta t has a value 0 for all positive times, and it has value 0 for all negative times. At t equal to 0, its value is non-zero, and this function has some amplitude which is actually not known. In fact, it tends to infinity, it goes to infinity. So the amplitude of the unit impulse function at t equal to 0 is actually going towards infinity, so we represent it by this arrow. But you should realize that the amplitude of this delta t function is not important, because we are not defining this delta t in terms of its amplitude. So we do not care what is the amplitude of this function, rather we are interested in what is the area under the curve. So the function is defined on the basis of its area, not the amplitude. This impulse function is actually a mathematically ideal function, and it does not exist physically. There are no physical functions which you can practically generate in a laboratory to actually represent a unit impulse function. However, there are number of conventional functions that can approximate, and they can have the properties of delta t whenever we have some limiting properties or a limit of some parameter that goes to infinity, that goes to 0. Say for example, if we have a pulse, if we have a rectangular pulse, say for example like this, and we have the area of the pulse, which is unit area. So if the area of the pulse is taken as 1, and if we try to reduce the width of the pulse, if we reduce the width of the pulse keeping the area constant, and reducing the pulse, of course would lead to a impulse function, because when you try to reduce the width, eventually you need to increase the height. So as you keep on decreasing the width, eventually the height would get increased, and if you have very small width, in that case this pulse would approximate an impulse function. So at this point I would take a simple problem to represent how we incorporate this impulse function in different types of calculation. So say for example, I want to evaluate an integral which involves this impulse function delta t. So we have an integral which has limits from minus infinity to plus infinity, t minus 3 square delta t dt. In order to evaluate this integral, you should realize that this delta t function exists at only one point, and that point is actually t equal to 0 for this case, because the argument is t. So this function exists at only one point, which is t equal to 0. That means this integrand, this entire thing, is actually exist at whenever we have t equal to 0, and for all other points this integrand would vanish. There will be the integrand would become 0. So if we substitute t equal to 0 in this integrand, in that case this integrand would become a constant number. So actually for this integration, this integrand is actually treated as a constant number, because it has a constant value, which is the variable has a constant value, which is t equal to 0. So if I substitute value t equal to 0 here, so I would see that I can be represented as 0 minus 3 squared, being constant. I have taken it out from the integral, and the integral is represented here from minus infinity to plus infinity delta t dt. This minus 3 squared is actually 9, so I have shown it here, and this delta t, integral of delta t, we know that this is the basic definition of impulse function, that the impulse function, whenever it's integrated, it will give a value of 1. So the integral of this delta t would be 1. So multiplying this to 9 into 1, so I get the value of integral to be equal to 9. So this is how we can incorporate this impulse function in different calculations. For a practice problem, I have given another integral, and I want you to evaluate this integral, and the answer is given as 4. For this integral, you should realize that this integral does not exist at t equal to 0, rather it exists when t minus 1 is equal to 0. because the delta function exists whenever the argument becomes equal to 0. So this integrand would exist at a point when t minus 1 would be equal to 0. This is one hint from my side in order to evaluate this integral, and after that you may be able to evaluate integral. So with this we would conclude today's lecture. We have discussed different single-sided and double-sided spectrum, as well as we have discussed different special functions that are used in analysis of communication system. Namely, we have discussed unit step function and signum function and unit impulse function. So we stop here. Thank you all.